approximately 150 million kilometers or 93 million miles away, and with the Earth with a radius of 6,371 kilometers or 30,959 miles. These sizes are too great to work with in most typical computer graphics programs. This experiment, the nature of typical CG lighting in a, quote, realistic render package is problematic because they typically have a light intensity fall off baked in. As you get further from the subject, the light intensity has to dramatically increase. At the distances proposed by this globe model, the CG programs really can't adequately represent them. The early days of CG lighting, there was a concept of it's called direct lighting, which basically the light doesn't lose power based upon distance. The light itself also has parallel rays and is supposed to simulate the sun from far distances. Luckily, we can replicate the sun in this experiment with a direct or infinite light. See here the harsh shadows that are cast, and as I move the light away, there is no effect on lighting intensity or the shadow sharpness. What does affect the shadow is the angle of the light. So this will be adequate for this experiment. So I built the model with two known caveats. The model would be scaled and the sun would be a direct light with the infinite parallel rays. Overall, this is not a compromise because the experiment is really to see if the globe/ball would also cast a shadow on the clouds as the sun went down. It's really important to build a replica as much as necessary. These principles are really about angles, line of sight, etc. So the essentials to do this, in my mind, were as follows. A scaled Earth globe, a suitable light source such as direct CGI, a cloud layer, a scaled version of the mountain, and really the approximate location and orientation of this photo, the point of view from which this whole thing took place. So the next question was, where was this photo actually shot from? Looking at the site, you can see Mount Rainier in the background. Another prominent feature was the building just in the foreground. It's next to this small body of water. It turns out that it is the Theus Landing Waterfront Apartments. Also, another noticeable feature was the Tacoma Dome in the middle ground just to the right. And then just in front of that was the East 21st Street Bridge. So with all of these locations determined, I could look at a map now to try and approximate this photo location. So looking at Google Maps, we see here the Tacoma Dome, and if you pan a little bit north, you'll see the East 21st Street Bridge. And if you pan a little further north, you'll see this building here that's shaped like an E. It's the Theus Landing Waterfront Apartment. And if you look at the ground photo of the building, it is in fact the exact building. So if you pan the map up in the line of sight direction, you'll find this building here, which is the Tacoma Sign Company. So while I can't be 100% certain this is where the photo was taken from, it's definitely precise enough for this experiment. So if you zoom out over the whole entire site, this area is what I needed to replicate and build in 3D. Looking at the overall map of this site, we can get some rough dimensions from the location of the photo to Mount Rainier. The distance away from Mount Rainier is approximately 68.2 kilometers or 42.37 miles. You can also see a Google Map 3D view of the site with the prominent features in the frame. So here's the sphere Earth model scaled 1 kilometer to 1 meter. You can see here the radius is 6,371 meters. As we zoom way down into the model, we'll see Mount Rainier. All of this data for Mount Rainier and Tacoma are from DEM data sources, and they have been scaled to 1 kilometer to 1 meter. Now zooming over to Tacoma, you can see the dome, the East 21st Street Bridge, the Theus Apartments, and now you can start to see the location where the camera was placed in this model. So here I will select the camera that was actually set up to view the scene. And you can see now here is our final shot. For verification purposes, I've placed a couple measurement references in the scene.
Yo,
this first one is the height difference in the model from the photograph to the peak of Mount Rainier. You can see that it is 4.378 meters. Mount Rainier is 4.392 meters above sea level in our model, so our camera is placed approximately 14 meters above sea level. Now we can select on the measurement reference for the distance away. You can see that the length is 68.2 meters or 68.2 kilometers scaled. And this reference is very close to the peak of Mount Rainier. Finally, taking all this information into account, let us compare our scene setup with the actual photo. For this experiment, this is more than adequate to demonstrate the concept of a globe bulge shadow. So here is a final render of the entire site based upon DEM data. The scale is correct and the geometry is correct. The site is ready for our experiment. For our experiment, we will be doing a sunrise. Now let's discuss the concept we're trying to demonstrate. The sun is supposedly located 93 million miles away. This distant sun creates a terminator line from the edges of the sphere. This terminator line or bulge shadow represents where the shadow is cast from. So as the Earth rotates, the terminator stays with the sun. For the demonstration purposes, we're moving the sun in this example. This is what happens from a point of view on the Earth. As we zoom in closer, we see our Mount Rainier location and the terminator line interacting with it. And as we zoom even closer, we can see how the terminator line / bulge shadow interacts with the mountain. Now let's add a cloud layer reference line. Where the bulge shadow crosses the cloud reference line, this is where you might expect to see the bulge shadow on the clouds. So based on these angles, the bulge should show up on the clouds in our experiment. Now we arrive at the scene. It's early morning and the sun is rising in the east. The conditions are perfect to see this rare phenomenon of the mountain casting the shadow on the clouds. Let's see what happens. As you can see, as the sun rotates up, it does in fact interact with the spherical Earth and cast a shadow on the clouds from underneath. Our experiment was set up to mimic the Earth as a sphere, the exact size and conditions for a shadow from Mount Rainier on the clouds, and the hypothesis that as the Earth rotates, the sun goes down below the Earth. If the Earth were a ball, this is what we should see under these special conditions. In fact, if the Earth were a ball, we should probably see this almost every night in some fashion or another. For a closer look at what's going on, let's go back to the schematic. If we pause the sun rotation right here where the shadow crosses the cloud layer just to the west of the mountain, here is the image of what we could expect to see. This experiment is a serious blow to the globe model. After working through this experiment, this is another in a long list of proofs that people can do for themselves. Each one of us can go out each morning at sunrise or each evening at sunset and observe this for ourselves. Do you see this shadow across the sky? For me, I've never experienced this visual in my life on this plane, nor have I seen any photos of this phenomenon to date. What I love most about the flat Earth is that it literally is right in front of us, and it points to our Creator and King. I was always a born-again believer, but flat Earth just adds that much more enjoyment to my appreciation of His creation. Every day when I'm outside, I look at this plane with so much more wonder and amazement, knowing that our Creator is right here, right above us, and we are the center of His eye.